This might be a little bit shorter of a class because we're just going to kind of work through the rest of those problems on that one practice exam and just do a few from the other. We'll kind of see. So just to kind of mention a few things. So I think I said a lot of this last class, but the exam will be kind of showing up on Canvas. It will be available from Monday at 9 will be when it's released to the end of the day on Wednesday. Once you get on and start it, you'll have 2 hours to complete and submit the exam. You've got 15 multiple choice, 2 short answers with 4 or 5 parts to each one. Uploading your work from whether it's a picture, Word, Excel. And if you do have multiple documents, I will have it so I believe that it will accept multiple files. But if not, feel free to kind of email me the second one immediately after kind of completing the exam, and I can kind of match up the times to when you finish the exam because I can see that. So that kind of covers the final there. I also, any questions we don't work through today from the other practice exam, which is practice exam A, I kind of posted that practice exam, the questions that we worked through between last class and today. We'll cover all of practice exam B's questions. So you'll have that additional resource. Oh, if I can get over here. I have put up the answer key to the 4th Excel assignment, which I said might be good for some review. And then we'll have a very similar thing for the 5th after today because the due date for the 5th Connect and 5th Excel is today. I will start trying to get those 5th Excels graded and then get up on Canvas something similar to what I did for the Learn Smart in the online quiz, where I show you what your grade in that homework category was with the lowest score from it dropped. Okay. Any questions related to the exam? Oh, the other thing I will have in the exam title, but similar to the other ones, don't use Safari. Some of those equations might not show up to you if you do, so make sure you're trying to use Firefox, Google Chrome, or Internet Explorer. Any questions for me kind of related to, anything about the procedure or anything like that, and not a specific problem like on a practice exam, but something specific to the exam?
So the exam is on Canvas still, right? Or will that be, okay.
Yep,
Cool.
It'll be releasing on Canvas at 9 on Monday. Yep. It'll show up it'll look like it's an assignment, kind of like the first 2 exams did.
All right, sounds good.
Yep. Any other questions? Okay. So we were on, which one were we doing? Was this practice exam? Yeah, so we were working off practice exam B. I believe we worked through 1 through 4, and then we skipped down and did a bunch of linear regression stuff with 7, 8, and 9. So I will come back here and kind of start working through problem 5. Okay. So on problem 5, we've got this example where the university has some policy where after 12 credit hours, you don't have to pay for additional credits. So we sample 35 individuals. We find the difference for each of those 35 people, then find the average difference, and the average change or the average difference in credit hours taken before and after this policy was 1.25. We have a sample variance for that difference of 13.2, and our sample size is those 35 students. So we've got some other information, but for this first problem, it doesn't impact us. So let's just say we want to calculate the test statistic for the above hypothesis test, right? So we have that it's greater than 0. We're always going to be using 0 as the assumed true difference here. So when we look at that formula sheet, right, sometimes we'll have people say, well, there's just a lot, I don't know which formulas to use. Well, if I'm writing things like this on the exam, which I will, if I show you that here's the average difference, look at that D bar, and even if I don't know what anything means, I can at least say, okay, well, I know it's going to be one of these 2 equations. This is a confidence interval equation, so hopefully we don't pick that one, but, at least matching it up to what equations we should use, matching the notation is just the simplest. So here's my test statistic for the average difference. It's really just a matter of plugging our values in for that, right? So I'm going to switch this over. as we're working on this, the dot cam. Okay. So here's my equation. I'm really just writing this out in the context of my example. So my average difference was 1.25. The variance was 13.2, and the sample size was 35, right? It's really all we're doing. I mean, this should be a relatively easy one, okay? So I think if I do that, I believe, and I'm writing that into my calculator, I'll get that 2.035. Okay? So in identifying the correct formula, I mean, like I said, try to match the notation, and I'll show you this on another example we worked through today as well. Okay? So here I've got a question about the p-value, but before we go ahead and do that, let's say I had asked you, maybe this was like the short answer or something like that, and let's say I ask you for, well, I was hoping it would all be on one line, but what if we were looking for the critical values at our kind of typical benchmark values? Actually, no one's in here. I'm going to take my mask off so I can talk a little better. So what are my critical values, right? Well, I've got the 5 or 10, 5, and 1% level. Anytime we're dealing with matched pairs, and kind of the formula sheet reminds me of this, but I'm dealing with that student t-distribution, and my degrees of freedom goes back to n-1. So when I'm looking for critical values, all right, and I believe that we had this was I already forgot. I should have pointed that out before I switched off the screen. So I've got a greater than sign in my alternative hypothesis. So I have a greater than or a right-tailed test. So I'm thinking about this student t-distribution, and I want the critical value that gives me kind of alpha in this tail. So alpha of 0.1. And then I'll have another critical value that corresponds to an alpha of 0.05 and another critical value 0.01, right? And this is what the 10, 5, and 1% significance levels. Okay. Once I find those values, my rejection region, it's a right-tailed test, will be the area to the right. Okay. So how can I look these up? So there's two ways, right? So the first way is, so go to my student t-table. There's only one way we're going to do this. I'm already thinking of the next example. So the areas that I want in the tail were what? 0.1, 0.05, and 0.01. Okay, so these three columns. My degrees of freedom would be what? Well, it's n-1. My sample size, remember, was 35. So my degrees of freedom is 35 minus 1, or 34. So the degrees of freedom of 34, my first critical value is 1.307. The next one is 1.691. And then the third one is 2.441. Okay. So I've got now my three critical values. And I should have known right away for a right-tailed test that they were positive, right? Because my student t-distribution is centered around 0. Now, if I'd had a left-tailed test, it would have been those exact same three values. I would have looked them up the exact same way. But because it's a left-tailed test, they would have been negative. Okay? So I would look them up the exact same way, but they would just be those values, but negative. Okay? Now, the test statistic that we found was 2.035. So if I'm thinking about, okay, where would that fall? 2.035 would be right about there. So it's in the rejection region at the 10 and 5% level, but not quite at the 1%. So we would fail to reject at that 1% level, reject at the 5 and the 10. Okay. Any questions on that before we keep moving here? Okay. So I believe the next question then says, okay, assume that that test statistic you found was 1.307. Okay. So assume we have this was our test statistic, and we're using an alpha of 0.05. What would be our p-value in our rejection decision? Okay. So what we're thinking about, just as a reminder, is we've got this student t-distribution. I just found 1.307 was my test statistic. The p-value is the probability that I see something as far away from the assumed true value as I did, or anything further that goes against the null. Okay. So I'm going to look up that area to the right of 1.307 on my student t-table. Now notice my degrees of freedom is still at 34. So I go over, I would have to give you one of these values as the exact test statistic. I'll never like ask you to do one that's in between to where you have to put a p-value in a range. So 1.307, the area to the right of that is 0.1, right? So my p-value here is 0.1, right? And if my p-value is 0.1, is my p-value less than alpha? If it is, I reject. Well, my p-value is 0.1. My alpha was told me to be 0.05, so I would fail to reject, right, at the 95% or the 5% significance level there, okay? So 0.1 and I fail to reject. Right. Now, what if this had been a two-tailed test? So if this had been a two-tailed test, everything would have been exactly the same, but it would have been equally as likely for me to see something that many standard deviations below the null that would go against it. Because if we had a two-tailed test, sorry, not a coefficient, we're looking at the difference. If I found something below, it also goes against the null. So now I have an equally sized tail on both sides. So if this tail is equal to 0.1, my total p-value would just be that times 2. So I'd have a p-value of 0.2. No, I didn't have a two-tailed test, but I'm just saying on the exam, if I gave you an example where you had a two-tailed test like that. Okay? Any questions on that one before we keep moving? So we went through a bunch of this last class. I think we did 11 at the very end. But let's look at number 10. This one might be a little bit more difficult even than the question I would ask you on the exam. But I'll kind of use it so that if we could do this one, we definitely can do anything that's on the exam. So let's say I want to estimate the relationship between median ACT scores, that's my Y variable, and the previous year's, so their athletic department expenses. So usually this is an example that we go through in class. We did some different data sets this year because I asked you guys and kind of solicited you for some ideas. But so let's assume that this expense variable is measured in hundreds of thousands of dollars, right? So it's not, the unit is not $1. 1 unit would be $100,000. So we find this slope coefficient of 0.3. What would the interpretation of that slope coefficient be? Okay. So kind of the setup we're thinking about is I've got my Y variable, which is kind of the ACT, median ACT score at a school. And then I've got my X variable, which is kind of the expenses on their athletic department. Right? So the way that we were told that this was 0.3. So the way that we interpret these slope coefficients is a 1 unit increase in my X variable is correlated with this change in the, increase or decrease in my predicted Y variable. So here, if the unit is $100,000, an increase of $100,000 is kind of correlated with a 0.3 increase in that school's ACT, right? So if I'm looking at kind of the responses, I'm trying to get something similar to that. So a $100,000 increase in, or sorry, it wasn't the athletic department. I had men's basketball here, but that's what I meant here. So in the men's basketball team or the athletic department, right, is correlated with a 0.3 point increase in ACT score at the university. Okay. So that's kind of that general form of that interpretation. It's more likely that instead of asking for an interpretation, I might do this in like a short answer. So I don't give you options. Like you should be able to kind of come up with this interpretation even for a short answer question. Okay. So some other questions that I could ask. Let's assume that we found, I don't know, that the intercept was 10, right? So how would I interpret the intercept? So the way I interpret the intercept is always if the X variables are equal to 0. Now I don't have more variables here, I only have 1, but even if I had multiple, it would be if all the variables were equal to 0. Here, the intercept is the predicted value of our Y variable. So if a team, or if a, university spends $0 on athletics, predicted, I can't spell, predicted ACT is, 10, right? And that might be, well, that's super low. Well, yeah, that's because in practice, we don't see any, university spends $0 on their athletic department, right? But that's still how we interpret the intercept, okay? So slope coefficient interpretations, intercept coefficient interpretations, and another very likely thing I could ask you in a problem like this is assume a team is spending we'll do $800,000 on their athletic department. What is the predicted ACT, right? Well, this one's a little bit trickier than probably one I would give you on the exam because remember, the units of expenses are $100,000. So if I have a team spending $800,000, that's really only kind of like 8 units, right? An increase of 8 units. So now, once I have that extra plugged in, it's just a little bit of math. 10 plus 0.3 times 8, right? So we would take that intercept coefficient, add to that the slope coefficient times, right? This 800,000 is 8 units there. On the exam, I'd probably just keep this as dollars, so I wouldn't have had it measured in hundreds of thousands of dollars just to make it easier. But right, we do this, so that'd be what? 12.4 if I'm doing this math in my head correct. Okay. So that slope coefficient interpretations, intercept coefficient interpretations, making predictions with a hypothetical X value or X values if I have multiple variables there on the right-hand side. Okay. Any questions on that one? I know I kind of threw that in some additional questions there. So this final one is one that I'll often have questions that look similar to this, and it should be relatively easy. So anytime, excuse me. Oh, sorry. So I find the estimate of my slope coefficient for the men's basketball expenses is 0.5. So instead of that 0.3 we had earlier, maybe, to keep it easier, we'll just think about it's 0.3. So we keep it consistent. And it has a corresponding p-value of 0.003. So a researcher concludes that if a team spends more money on their basketball program, the expected ACT score will increase the following year. So they should just spend more money, right? So what's wrong with this logic? Well, thinking that there's nothing wrong, it's not going to be the issue because saying regression results imply causation is wrong. We need to remember that these estimates, right, these slope and intercept coefficients we're coming up with, they're only estimates and they're only evidence of correlation because if there's other important variables I'm leaving off that are correlated with both these things, I'm going to have a biased slope coefficient. So it's only evidence of a correlation, not necessarily causation, right? It could be that X2 is causing expenses and ACT scores to go up. Right? That was that omitted variable bias. So if we're looking through these answers, the results are not significant. Well, actually they are. So that's not the reason why this logic is wrong. The regression results only provide evidence of correlation. There may be omitted variables that are both correlated with team expenses and our Y variable ACT. That's exactly what I just said. Right? Could be that we are leaving out other important variables on the right-hand side, or these independent variables that are driving both of these things, right? So it's just evidence of a correlation. Okay. Any questions on that? All right. So let's go to the other practice exam. So practice exam A. And something we didn't work through on this one that I kind of worked through with my other sections. I wanted to make sure we went through some stuff, kind of show you a couple things I think will be helpful. And I'll probably go through them relatively quick. A lot of it's, I'll kind of skip on some of the computation. Well, let's say we had an example like this where I've got 500 men, 500 women. I've got 37% of men owning guns, 31% of women. So I give you kind of here, group 2 is women, group 1 is men. Here's their sample proportion. What's the 90% confidence interval? Well, I mean, if we look at our formula sheet, once again, I gave you sample proportions. So when you're looking at these automatically, say, okay, here's one that I could be using. Here's one that I could be using. Those are the only 2 that you should even think about applying to this problem. And then I remember, oh yeah, I'm asked for a confidence interval. I need to have a lower and upper bound. I'm trying very hard here to show you these are the confidence interval equations. So this should be the equation I use. I plug in 0.37, 0.31, 0.37, 0.37, 0.31, 0.31, 500s. I can plug everything in. It's just a matter of computation. The only thing left is really looking up this z-value. Okay? So what am I doing when I'm looking up this z-value? Well, I'm thinking that I've got this confidence interval, and really what I want is alpha total outside my interval or alpha over 2 kind of on each side. Right? And I want to find this z-score that gives me alpha over 2 in each tail. Okay. So I think the alpha that we were told here is the 90% confidence level. So my alpha would be 0.1. So 0.1 over 2 is 0.05. Now also, I know that I'm using the standard normal distribution because anytime I'm dealing with proportions, and my equations kind of remind me, proportions means I get to use that standard normal distribution. Okay. So I go to my z table. The area I want in the tail is 0.05. Right, so it's just a reminder, 0.05. So in between these two, negative 1.64 and negative 1.65. I'll use the higher of the two, right? But I have to kind of remember it's not negative 1.65 is that value I'm looking for. I just want the absolute value because my confidence interval equations already have the positive and the negative signs built in when I'm adding that margin of error to my upper bound and subtracting that margin of error to my lower bound. Okay. So once I have that z-score, now I've got everything I need, and now it's just a matter of getting it entered into our calculator. Okay. Now, one kind of trick or thing that can make that easier, calculate this component ahead of time. This represents the standard deviation for the difference. But if we go ahead and calculate that ahead of time and then just plug that value in, kind of breaking it up into steps, that can make it a little bit easier. I think if we end up doing that computation, we should get 0.011 as our lower bound, 1.109 as the upper bound. Any questions on that one? Like I said, I'm not going to write it all out, just kind of showing you the parts that really, to get all the components you need, then you kind of just plug and chug. So what if I'm looking for the test statistic for the following hypothesis test for gun ownership between men and women? Well, once again, go to my formula sheet. I've got sample proportions. Here's my test statistic equations. Well, then this is the one I'm going to be using, right? Because I'm looking for the difference in sample proportions. Okay. So one thing that we can think about when we're dealing with this test statistic, I'll write out the general form here real quick. Okay. So in all of our test statistic equations, the denominators represent standard deviations. Variances and standard deviations are always positive, right? So the sign of our numerator, because we don't really have an assumed true difference anymore, right? I told you on the exam I'm only going to use 0 here. So the sign of my numerator is going to tell me the sign of my test statistic. If it's positive, positive over positive is a positive test statistic. If the difference is negative, negative over a positive would be a negative test statistic. So the sample difference I found here, 0.37 minus 0.31, is 0.06, right? So I should know automatically that my test statistic is positive, so I can rule this negative value out right away. Now, if I'm just guessing from here without plugging everything in, I found a sample difference of 0.06, right? That might not seem like much, but for proportions, what's the largest difference I could ever see? Well, that would be if one group had a proportion of 0 and the other had a proportion of 1. So the greatest difference I could see is 1, right? Well, here, 0.06, so it's not that small. So my guess is it's more than 0.03 standard deviations away from that assumed true difference of 0. So theoretically, this is a possibility, but I doubt it, right? So from there, it's just a matter of plugging everything into those equations. So I'm not going to kind of write all this out, but we've got our 500s for sample sizes, 0.37, 0.31. whatever that P bar is, I plug that in, plug in my 500s as my sample sizes. We already talked about the numerator. It's really just a matter of computation, okay? So if you do that, I believe you will get, oops, 0.2002. Okay. So here we've got this test statistic. Similar to the last one, the matched pairs problem we're looking at. What if I asked you for the critical values at all levels, right? Okay. So if I wanted the critical values here, and I've got a two-tailed test, right? What I'm really thinking about doing is taking this student t distribution and first finding kind of the, right, critical values that give me alpha total in the tail. So I want the critical values that give me alpha of 0.1 total in the tails, so 0.1 over 2 in each tail, right? And actually, sorry, I wrote a t here. That was wrong. We switched exam. We're now looking at the difference in proportions. So these should be coming from a standard normal distribution. Okay. So I'm looking for a z value that gives me alpha over 2 kind of in each tail. Okay. Now I could look this up, right? I could go look up 0.05. You know, we actually already kind of did a similar thing earlier. For the confidence interval. So I find what's close, negative 1.644 and 5, 1.65, right? Or another way I think is be easier to do this is think about what our three alpha values are. So 0.1, 0.05, and 0.01. So to find my critical values, I'm going to look up alpha over 2. So the areas I want in the tail will be 0.05, 0.025, and 0.005. So here's my three kind of critical values. Or sorry, here's my three areas in the tail I want to use to find the critical values. So I go, instead of looking each one of these up, right, individually on this standard normal table, I can kind of cheat and use the student t. The areas I want in the tail are 0.05, 0.025, and 0.005. But if I go all the way down to this very last row, remember, this shows me what those standard normal values would be. So I look at those three columns that had the areas of 0.05, 0.025, and 0.005. And I get that my critical values will be plus a positive and a negative 1.645, positive negative 1.96, positive negative 2.76. Just grabbing those very quickly from this last row of that student t table. So if we can kind of remember that that last row gives me the standard normal values, it makes a problem like this a lot easier, okay? Any questions on this? So I'm kind of adding this question and it wasn't there before. So, I could set this up and, well, that's not going to work. I'll try to have these right here. There we go. So I could, set this up where I draw the rejection region for every single level. So let's go here, here, here. So this is what, 1.645, negative 1.645, negative 1.96, 1.96, 2.576, negative 2.576. My rejection regions, right? So I've got a pair of critical values at every single level. I draw in kind of my rejection regions, which is the area that's more extreme than those critical values. I can kind of remember this corresponds to 10, 5, and 1% significance level. If this was a short answer question, I asked you, find the critical values, and then I said, find the p-value, and then I asked you, make a rejection decision using either approach, and you chose the critical value approach, you would then take your test statistic, I think it was 2.035, which is just inside, right, of that rejection region. So you can reject at the 10 and the 5% level, but not quite in the rejection region at the 1% level, so you would fail to reject there. So that's how you'd use those critical values, right? You've got a two-tailed test, so there's a pair of critical values at each alpha. Once you find them, you can kind of plot your test statistic and figuring out whatever rejection regions I'm in, I'm rejecting. If I'm not in the rejection region, I fail to reject. Okay? Any questions on that one? Okay. So the next one is probably something more similar to what you might see in the exam, where I'm going to give you an assumed true test statistic. I'm going to then ask you for the p-value and the outcome of the test. Right? Well, here, right, I've got a standard normal distribution. So if I've got my test statistic of 1.45, and I'm still dealing with a two-tailed test. Okay? So what I'm thinking about is I found this test statistic of 1.45. Typically, the p-value I could think about is the probability I saw something that was this many standard deviations away from the assumed true difference, or anything even further. But that would be only if it's a right-tailed test. Because it's a two-tailed test, it would have been equally as likely that I saw something this many standard deviations below that assumed true difference, or at even further. But now, because I'm assuming the difference is equal to 0, evidence on either side, right, would go against that assumed true difference of 0. Right? So this will only be half my p-value. The other half is over here. So once I find this area, I would need to multiply it by 2. Okay? So I'm going to look up that z-value of 1.45. So I go to my standard normal table, z-score of, scroll down here, 1.45, so 0.9265, right? So 0.9265. Now, I drew this in. Remember, what the value I looked up is not the area in my tail. It's the area in the left tail. So if I look up positive 1.45, and then I forget and think, oh, okay, the area in the right tail is 0.925. I multiply that by 2. I get 1.8 something. I should know that I made a mistake. I saw a lot of people make this mistake on the Excel, and they didn't, I guess, didn't realize it, or maybe they just didn't know how to fix it. But if you have a p-value that's over 1, it's impossible. The p-value represents a probability, right? So if you multiply this area you found by 2 and you get 1.8, oh, I forgot to do something. I must have made some mistake. Sure enough, the area that you were wanting was the area in the right tail. The table told you the area to the left. So you have to subtract that from 1, right? That ends up being 0.0735, right, is the area in this right tail. You would then multiply that by 2, and that would give you your p-value, right? So if we do that, if I can get this paper, come on, sorry. So 2 times 0.0735 is 0.147, and that's my p-value, right? Oh, sorry. So if I'm using the p-value approach, I only reject if the p-value is less than alpha. And I think in this problem, it asked at the 5% level, but we could test all of them pretty quickly, right? If I've got my p-value here, is that less than 0.1? Nope, so I failed to reject. Is that less than 0.05? No, so I failed to reject, and it's not going to be less than 0.01 either. So I failed to reject at all levels here. Okay, and the reason why that didn't line up with our critical value approach earlier is because, remember I changed it to give you that assumed true test statistic. So we were really kind of using 2 different test statistics there. Any questions on this one? Okay. So that kind of takes us through those. Oh, I want practice exam A. So we've got some more matched pairs. I've got a couple more things that I want to say, but I know we're not going to have time to work through all these. So Are there any questions that you might have for me on the kind of questions that could be asked in the exam? Maybe something that's kind of been tripping you up or? Okay. So a couple things that I wanted to mention. Down here on this regression output, I can't reiterate this enough because I just want to make sure I cringe every time I see someone get it wrong. But one of the easiest questions on the exam, some of the easiest points that should be available to you is when I'm asking you to calculate a test statistic for a coefficient. And in the past, like I see people get this wrong. I guess I don't understand, because if we look at how do we get a test statistic on a slope coefficient, I'm even kind of giving you that formula. It's as simple as taking that coefficient estimate and dividing it by the standard error, okay? So if I'm looking at this here, for all these variables, how do I get these test statistics? I simply take that coefficient estimate and I divide it by the standard error. I can recreate each one of these test statistics by simply dividing this column by this column, right? That should be the easiest points in this exam. I would hope I see nobody missing those if I'm asking you to calculate a test statistic for a slope coefficient, okay? Additionally, if we're thinking about making rejection decisions, like which variables have a significant relationship, remember I said last class having a significant relationship with the y variable is the same as saying we can reject the null, right? Because the null is always that slope coefficient is equal to 0. So if I'm rejecting this, what I'm really saying is that the slope is not equal to 0, or there is a significant relationship between x and y, right? Because remember, this slope is coming from this equation. So if this is anything other than 0, there's a significant relationship between x and y. Okay? But if I'm trying to make this rejection decision, this output here is a little bit easier. If we looked at practice exam B, which is the one I think we worked through in class, remember, there's going to be some that, if we see these e to the negative, that's a p-value of basically 0, okay? So be careful with that. Anytime you see an e to the negative, you might as well think about that's a p-value of 0. Now, on the exam, I'd likely, I might have some p-values that show up like this, but one thing I won't do that we have up here is I won't give you a standard error that has like e to the negative, because then it would be kind of harder to calculate the test statistics. So the output is more likely to look like this, right? The practice exam A output for the coefficients and the standard errors. But I just want to make it known that for the p-value, it still could be that you see it more like on practice exam B, where some of the p-values have e to the negative, which basically represents this is just 0, right? Move that decimal point 73 places to the left. Okay. Yeah, so that might, be something that you want to kind of pay attention to. Kind of already went through, the types of questions I'll ask you for linear regression. Is there anything else I wanted to mention from this other exam? So that slope coefficient, just another matched pairs example, another sample variance example. So should just be more practice if you're going to want to work through some of these on your own. But like I said, I also put that video up on Canvas, so you could watch me kind of work through the rest of those problems. One thing I'll tell you, because if you showed up to watch the Zoom, or anyone who I guess watches this video in retrospect, I threw on some additional problems just like I did last class in the linear regression example we worked through. So this one, even though it says 9 through 10, I added like 3 or 4 different problems there to the linear regression part to give you example problems of what I could ask on the exam. And if I'm the one that wrote the exam, I would probably pay attention to things like that. So that might be a good thing to kind of watch the very least the end of this video that's up on YouTube as well. Okay. Other than that, I think if you guys have any other questions, I can answer them. Otherwise, we'll probably kind of call it there today. I made sure we got through those kind of difference in sample proportion examples. Now, one thing that's not on either of the practice exams, and I can't remember if I mentioned this last class, but you should review, is how we deal with differences in sample means when we know the population variances. It's really like very similar to what, it's kind of the combination of what we did with sample means and sample variances, like the format of the confidence interval and the format of the test statistics look more similar. It's just that when we have known population variances, looking up critical values, looking up p-values, it's very similar to when we had proportions, because now we're going back to using that student t, or standard normal distribution, not the student t distribution. Any other questions from me? Nothing? All right. So I will be keeping an eye on my email today and this weekend. This weekend, I can't promise a response, within 10, 15, 30 minutes, but I will be checking my email occasionally and trying to get responses out to you as you're studying for the exam. Also Monday, Tuesday, if you're waiting to kind of later till in the week on Wednesday to take it, I'll be working all those days. So I'll keep an eye on my, I'll be keeping an eye on my email. And other than that, I think that should kind of be it for the semester. I'll be grading those Excel 5s and getting scores updated on Canvas as soon as possible, or this weekend and early next week. And other than that, thanks for, I know we're still doing kind of hybrid, but, I didn't get to see as many of you all the time, but thanks for a good semester. Always feel free to kind of reach out if you need help with anything kind of down the road as in your college career. And good luck studying for the final. I hope everybody does well and has a great summer.